Hello, and welcome to the lecture for Chapter 17, where we're going to discuss change of phase, like going from a liquid to a gas. This is the third chapter in our discussion of heat and thermodynamics. Okay, so let's get into it. All right, so we're going to define phases, the hopefully well-known phases of matter, but just review them. Then we're going to describe what is evaporation and condensation, the physical meaning of them. Talk about how boiling is a phase change, but under very specific conditions. Talk about generally melting and freezing. And finally, finish off by quantifying the energy of changes in phases. So what's the number that we can assign to a change in phase? All right, basically, how many joules does it take to change phase? Okay, so matter exists in 4 common phases. They are a solid, a liquid, a gas, and a plasma. Okay, all right, so a solid is like ice. All right, when ice melts to water, it becomes a liquid. This being an example, of course, of H2O. And then eventually that water can vaporize into water vapor. All right, or just known as vapor. And then finally, that vapor can disintegrate into ions and electrons. Okay, and in order to reach a plasma phase, there would be no molecules left. Okay, so it wouldn't be water anymore. It wouldn't be H2O. Because in order to become a plasma, the H and O's would have long since split up into individual atoms. And once they split into individual atoms, which is dissociation, then they can be ionized. Okay, they can disintegrate. And then all that's left behind are the nuclei and the electrons. Okay, now this is not enough energy to actually cause fission, right? So, but which would be splitting up of the atomic nucleus, but it is a highly energetic gas, a plasma. Okay, and it has some distinct characteristics, so we define it as another phase of matter. But it requires a lot of energy, so we will not be talking about it much in the rest of the lecture. So the big 3 are going to be solids, liquids, and gases. All right, so the phases of materials depend upon the temperature and the pressure. All right, so you could heat something up, or you can pressurize it in order to change its phase. So the process going from or requiring an input of energy is, of course, solid to liquid, then liquid to gas, and eventually gas to plasma. So if you continue to input energy into a system, that is the direction of phase changes. Energy causes the molecules to move more rapidly, and that's why they eventually will undergo these phase changes, changing the very way that they interact with each other as they start to bounce around more and more. All right, so let's understand evaporation. It is a change in phase from a liquid to a gas, all right? It is not a bulk change of phase, so not bulk phase change. So it's not the entire quantity of a material changing from a liquid to a gas, but only a few atoms, all right, or molecules. An example, of course, of water evaporation, or is water evaporation, where you could have a liquid water, shown here on the left, becoming water vapor because some water molecules near the surface are energetic enough to escape, have enough kinetic energy to become a water vapor. They may be overcoming the energy associated with surface tension. They may be overcoming the energy associated with just being, gravitationally stuck, right, and not just accelerating around. But some of them will have enough energy and they will become a vapor, okay? And then where do they get that energy? Through random chance collisions. Because through all the random collisions of these water molecules, some of them will pick up more energy than the others. They don't all have the same amount of energy. They have an average amount of energy, which we know is proportional to their temperature. And that would be an average amount of kinetic energy. So this is kind of summarizing the information. Molecules in a liquid move randomly at various speeds. Okay, there is some average, but there's many speeds within that population of molecules. Right, there are after all trillion of trillions of them, continually colliding into one another, as I mentioned. Some molecules gain kinetic energy while others lose kinetic energy during these collisions. Okay, it is a random or stochastic process is the name for that. Some energetic molecules escape from the liquid and become a gas. All right, average kinetic energy of the remaining molecules in the liquid decreases, resulting in cooler water. Because think about that, right? Because what happened is one of the most energetic escaped, meaning that the overall average that remains is lower. And if a single atom escapes from a huge population of trillion upon trillions of atoms, obviously that change would be tiny, but over time, the effect is significant. So water that is allowed to evaporate will cool down, all right? It is a cooling process, okay? So evaporation can have some important consequences for biological processes, all right? Such as when bodies overheat. So sweat glands create perspiration. The water on our skin absorbs body heat as evaporation cools the body, and this helps to maintain a stable body temperature. All right, so the idea, right, think about that. The water that has been put on your skin, if you are an animal that sweats, like this pig, or a human, and as that water that is being put on your skin as an evolutionary tactic that we have evolved because it was selected for success. Now that water on our surface, some of it, by random chance, will be energetic enough to evaporate. That means it's essentially taking away the body heat with it. Okay? Does that make sense? So it's leaving cooler water, thus cooler body behind. All right? So evaporation is a cooling process caused by the random collision of molecules. Okay? So evaporation can also skip the liquid step altogether in a process known as sublimation. This is a form of phase change directly from a solid to a gas. Examples are dry ice, okay, and mothballs, and sometimes frozen water. So certain substances have, when they are brought out of a very low temperature, dry ice being a good example, when they reach, say a room temperature of 20 Celsius or 293 Kelvin, that's such a big difference from their temperature required to keep them in the solid phase that they can basically have energy enough to undergo two instantaneous or simultaneous phase changes, going all the way from a solid to a gas. Furthermore, sometimes in certain situations, there's a large amount of ambient energy. So if you consider frozen water on an ice sheet at one of the poles of our planet on a hot, windy day, you have all the kinetic energy of the wind, and you have the radiation energy of the sun. And with that energy is combined in large amounts, the energy can be sufficient to cause sublimation, in other words, skipping of the liquid phase altogether. All right, so some of that ice can just sublimate into a gas. All right, so essentially at the molecular scale, there's molecules that are being broken free and torn off into the atmosphere due to the large amount of energy coming in from the sun and the wind. Okay? All right, so condensation is the opposite of evaporation. All right, it is a warming process from a gas to a liquid. Gas molecules near a liquid surface are attracted to the liquid. All right, they are attracted due to molecular forces. Right, they may just be falling under the influence of gravity. They strike the surface with increased kinetic energy, becoming part of the liquid. All right, so what happens is it's a collision. All right, condensation. It's going to collide with some of the water molecules that are already there. It's going to lose enough energy to not just rebound off the surface, but then instead become part of the liquid. Now, that's not to say that there aren't water vapor molecules that bounce off the surface of the water. There certainly are, and those ones remain water vapor, but there are some that crash, give up enough of their kinetic energy, and then become part of the water. But regardless, they're giving up their energy to other molecules, but those other molecules are part of the liquid water system, so the liquid water must become warmer, right? It absolutely warms up the water. Condensation warms up the water. Okay, so kinetic energy is absorbed by the liquid. It does result in an increased temperature because it results in an increased average kinetic energy of the molecules that make up that liquid. Steam examples include steam releases much energy when it condenses to a liquid and moistens the skin. Hence, it produces a more damaging burn than from the same temperature 100 degree Celsius boiling water. So 100 degree steam and 100 degree water cause very different effects on the skin because that 100 degree steam undergoes essentially a phase change, releasing a huge amount of energy. We'll talk about how we can quantify that large amount of energy in the last section of this lecture. And furthermore, you feel warmer in a moist shower stall because the rate of condensation exceeds the rate of evaporation. That's where you have that very noticeable warm feeling, even though otherwise being wet immediately makes you feel cold. Okay? Continued. In dry cities, the rate of evaporation from your skin is greater than the rate of condensation, so you feel colder. On the other hand, in humid cities, the rate of evaporation from your skin is less, so it's like the shower. Thus, you can't really cool off by sweating. All right? So, for example, if you're in a very wet, hot city, say in a certain part of the world, then what's going to happen is you're going to not be able to cool off. All right? You're going to feel hotter than you would otherwise in dry heat. All right, that's why people talk about how wet heat is harder to deal with than dry heat. All right, so dry, we have the advantage of releasing heat through evaporation, but it doesn't work in humid cities. All right, another example, a cold soda pop can is wet in warm air because the slow-moving molecules make contact with the cold surface and condense. All right, so every time you see a cold object, they start to get all the little water droplets on its surface, that's not because it's leaking water, okay? It's because water in the air, which otherwise would have been invisible, is colliding with that cold surface and giving up sufficient amounts of energy to phase change from a vapor back to a liquid, okay? So that's where the water comes from. It's not literally sweating out of the substance. Okay, all right. So condensation in the atmosphere, does it happen? Absolutely. When the temperature of the atmosphere is low, right, because low temperature is going to cause condensation, either because you're coming in contact with a low temperature liquid or solid, or just because the overall ambient temperature is low. The water molecules in the air move more slowly. Slow-moving water molecules can stick together due to molecular forces rather than bouncing off each other. All right, so here they are kissing. For example, fog and clouds are created when air rises. It rises and it cools through expansion, and that cooler air is then able to have condensation of all that suspended water vapor, because air always has some suspended water vapor, sometimes huge amounts. So if bits of coal do not stick to your feet when firewalking, it's best if your feet are, think about what we were learning here about phase changes, because it's true, we don't want it to stick, but we don't want to have a long-term process, because we learned, right, that it's due to the low thermal conductivity of coal that makes this possible in the first place, so we don't want them to stay in contact with our foot for a long time. But you can guess that then what you want is wet. That's because the energy that vaporizes the water is energy that doesn't get to your skin. All right, now you maybe noticed this before, wet hands. If you have wet hands, you're able to touch hot things, maybe just for a short time, but you're able to touch hot things that you otherwise would not be able to touch with dry hands, because having that water on the surface of your skin allows for that quick phase change, eating up energy that doesn't bother your skin. When you step out from a hot shower, you feel cold, but you can feel warm again if you step back into the shower. Which process is responsible for this? Which one is it? Which one warms you back up when you step back in? It is, of course, condensation. Because when you step back in, then you start to receive the heat from all that gas, all that hot water vapor. It starts to basically impart kinetic energy back to your skin, and you feel nice and toasty again. All right, so I said we talk about the specific phase change of boiling, all right? Because boiling, we think as well, it's defined as 100 degrees Celsius, it's a big deal, it's definitely a phase change, but it's not just any phase change. It is a phase change under very specific conditions, okay? And although, we might just think of it as, turning liquid water into gas or water vapor, that's not really what boiling is. Because in that case, then we could say that evaporation is a form of boiling. But we don't agree that those two things are the same, do we, right? Evaporation is a process that's slow. You leave a glass of water out, over many days it will slowly evaporate. Right? You leave your pet's dish out, the water inside slowly evaporates. The boiling is fast. It requires a lot of energy, direct flame. So they're different processes, right? Why are they different? Okay? Well, boiling is the rapid evaporation, and here's the key, from beneath the surface, okay? The phase changes we've talked about so far occur at the surface. Well, boiling does not, okay? That means that boiling requires a particular balance of forces. It requires the creation of air bubbles in which the internal pressure of that air bubble exactly equals the outside pressure of the water. And furthermore, it has to occur in a pot where this depth is negligible. Because if it was, say, like a meter deep, then the pressure is going to be affected by the depth. But as long as the pot is only a few centimeters deep, then we can ignore the hydrostatic pressure, refer back to our fluids chapter, and then the only difference is that essentially we need to make sure that we are achieving atmospheric pressure inside of these air bubbles. But to achieve atmospheric pressure inside the air bubble requires a lot of energy input, okay? And specifically requires that the temperature right here at the bottom is 100 degrees Celsius, okay? So, rapid form of evaporation beneath the surface forms vapor bubbles. Those bubbles rise to the surface and they don't collapse because their outward pressure, this red arrow here, equals the inward pressure from the liquid. Okay, that's the key idea, because otherwise they never make it to the surface because they collapse. We see that in liquids that are about to boil. We constantly see little bubbles forming. They appear to just be stuck to the surface of the pot, but in reality, some of them are breaking free from the surface of the pot, but they're immediately collapsing because they're not able to make it up to the surface. They don't have enough internal pressure to do so. Okay, so the vapor pressure in the bubble is less than the surrounding. That bubble collapses, never makes it to the surface. Hence, bubbles don't form at temperatures below the boiling point. So that's what the boiling point is a particular process of creating air bubbles, well, water vapor bubbles, really primarily just H2O in a vapor form because there wasn't any other molecules besides impurities in the water to really create that bubble. So water vapor bubbles that are being created through a phase change underneath the surface of the water. All right, so it occurs at 100 degrees Celsius. It is a thermal equilibrium process. Boiling water is being cooled as fast as it is being warmed. Okay, so once it's boiling, it's no longer heating up. Okay, that says absolutely, it is a process where it's able to lose just as much energy as is being inputted through the direct flame or heat pad or whatever it is that's boiling the water. Okay, so in this sense, boiling is absolutely a cooling process. It is releasing energy from the water. Okay, it is a mechanism that allows energy to be released to match the energy input. All right, so boiling point depends on pressure. The buildup of vapor pressure inside a pressure cooker prevents boiling, thus resulting in a higher temperature that cooks the food. Why is that? Well, because in the pressure cooker, we essentially put a top on here and we give a pressure. That means that the pressure here is the same as, say, trying to boil something at the bottom of a 10 meter deep tube or a 10 meter deep pot. Because if you wanted to do that, if you did want to boil water in, let's say, like a giant tank that was many feet deep, you would also have to account for that depth, as I said before, because that would be the depth pressure. But the way we do it in practice, the way we increase boiling temperature is by sealing the top and creating pressure in a seal on top. Okay. So the boiling point is lower for lower atmospheric pressures as well. So if we, instead of we could open it back up, but then consider that the elevation is going to affect the pressure. Thus, boiling temperatures are different. At high elevation, like in Denver, water boils at 95 degrees. If you were to go to the top of Mount Everest, you could boil water at, say, 80 degrees Celsius, right? So very, very much lower boiling temperature because the pressure, the atmospheric pressure, is much less there. All right, so here we see a demonstration of the cooling effects of evaporation and boiling. All right, so basically condensation building up. All right, so the process of boiling cools the water being boiled. Option A depends on atmospheric pressure. Option C is a change of phase below the water surface. Well, what do you think? Of course, it's all of the above. All right, so in general, melting and freezing. Melting occurs when a substance changes phase from a solid to a liquid. It is the opposite of freezing. When heat is supplied to a solid, the added vibration breaks molecules loose from the structure and melting occurs. Freezing, on the other hand, occurs when a liquid changes to a solid. It is the opposite of melting. When energy is continually removed from a liquid, the molecular motion decreases until the force of attraction binds them together and formation of ice occurs. Okay, so freezing requires a removal of energy, whereas melting requires an input of energy. Okay, so you can think of the random process we're going to lead to whatever equilibrium and the phases that will match the equilibrium. Okay, so energy and change of phase. From a solid to a liquid to a gas, you add energy. From a gas to a liquid to a solid, you remove energy. Right, so here is a diagram that shows the direction of energy and its relationship to phase. So examples of both vaporization and condensation processes. Cooling cycles of refrigerators pump a special fluid that vaporizes, and while it vaporizes, it draws heat from the stored food. The gas that forms, along with its energy, is then directed into a condensation coil outside the fridge, where heat is released and the fluid condenses back to a liquid. Of course, that requires the energy of the pump, which is why you have to pay for a refrigerator. Likewise, an air conditioner pump pumps heat energy from one part of a house to another. Okay? So as far as the energy and change of phase, there's something called the heat of fusion. Okay, this is the key term. It is the amount of energy needed to change any substance from a solid to a liquid and vice versa. Example, for water, it is 334 joules per gram. Compare this to specific heat. Specific heat was a quantity that told us how much energy it required in joules per gram per degree, because specific heat was a 1 degree change. But here, we don't have per degree in our expression of heat of fusion, which is also sometimes called the specific heat of fusion, to relate it to specific heat. But anyway, we don't see a per degree or a per Kelvin because it wouldn't be appropriate. This is independent of temperature because the phase change occurs at the same temperature. In other words, 100 degree water becomes 100 degree water vapor. There's no temperature change, there's just a phase change. There's only a temperature change after the phase change is complete. All right? So farmers in cold climates replace frozen tubs of water with unfrozen ones in their cellars to prevent jars of food from freezing, because that heat of fusion is so significant. It eats up a lot of the ambient energy around. Okay? On the other hand, the heat of vaporization is the amount of energy needed, maybe furthermore, is the amount of energy needed to change any substance from a liquid to a gas and vice versa. The heat of vaporization is even greater than the heat of fusion. It is 2,256 joules per gram. Okay? And remember, compare this to 4.186 joules, joules, uppercase J, per gram per Kelvin, which was the case for specific heat for water. And this is one of the highest specific heats out there. So, that's of course only per 1 Kelvin. So if I wanted to go 100 Kelvin, then it would be 418, about 418 joules to heat up water from 0 degrees Celsius to 100 degrees Celsius. That's liquid water. But then check it out. It costs 2,000, almost 2,300 joules per gram to then boil it. It costs a lot more energy to go from a phase change, okay? And especially a phase change from a liquid to a gas. If we look at the phase change from a solid to a liquid, it was about comparable, and in fact a little bit less, but about comparable to the entire energy to go from 0 degree liquid water to 100 degree liquid water. Because remember, that would be 400 and about 420 for rounding, okay? That's this number just multiplied by 100. All right, so a lot of energy in vaporization. So when snow forms in clouds, the surrounding air is, think about it, it is warmed because that process is releasing energy. Which involves the greatest number of calories. All right, so this is relating to what I talked about. Look at our options here. All right, read them over. Pause if you need to. I want you to have an answer on this one. This is one of the important quantitative ideas that come up in this chapter. Okay, condensing 1 gram of 100 degree steam to 100 degree water. Okay, so 1 gram of 100 degree steam Celsius to 100 degree water. Because remember, that's to over 2,000 joules. Okay, that's a lot of energy. That's way more energy. 540 calories is more than the 100 calories for B and half of the 273 calories to cool ice. All right, so big difference there. Okay? So ice is put in a picnic cooler to speed up the cooling of cans of beverages. It is important that, well, think about it. Of course, you need the phase change. The ice has to melt. So melting ice is the quickest way to cool things. All right. So that's it for our phase change chapter and our third chapter in our exploration of thermodynamics. Thank you so much for watching.